Alright, so hello and welcome. We're going to work on another problem. This is going to be burst balloons, hard, and on LeetCode. Give it a shot. So actually I thought about this invalid parentheses problem, and there actually might be a quadratic time solution. However, obviously that's not the one that I went with. It's not the one that I went with. I kind of want to move on. We can come back to it later maybe, but I'd rather not. I'd rather just work on some other problems. Could always come back to some of these. I think the idea for the invalid parentheses, I think you can do a what do they call that? A sequence-based approach, so similar to what we had done for the similar to what we had done with the stock buying question, stock buying solution. I think we could do a similar kind of approach to the invalid parentheses question. Basically, we can get all the sequences that are valid and do that using recursion and memoization, and then convert that to a DP solution. And then among the valid solutions, we can create our set of the minimum removed. What is it? The set of valid solutions that have a minimal number of parentheses removed in order to have valid parentheses. So yeah, that could be done. I think you can use a DP solution for that. That's what I'm trying to say. I think you do quadratic time DP solution. I think. I don't know though. I'd have to like spend some time on it, but I don't really want to spend that much time right now. Maybe I'll come back to it. I don't know. Think about it. Maybe I'll come back to it like in a few days from now or something. But yeah, there is a part of me that thinks maybe it can be done better, and maybe I should have done it quote unquote correctly the first time. You're given n balloons. You are indexed from 0 to n-1. Each balloon is painted with a number on it represented by an array of numbers. You're asked to burst all the balloons. If you burst the ith balloon, you will get nums times I minus 1 times nums of I times nums of I plus 1. Okay. Oh boy. Okay, the numbers between 0 and 100, but you have 500 numbers. Oh boy. Oh, okay. Excuse me. You get some multiplication in terms of coins. If I minus 1 or I plus 1 goes out of bounds of the array, then treat it as if there's a balloon with a 1 painted on it. Then turn the maximum coins you can collect by bursting the balloons wisely. I think all of these questions are some form of, like, not all of them, but some form of like sequence type of deal. Huh, well, that is interesting. So let's see. We've got to be somewhat efficient here because n is between 1 and 500. That's interesting. So this is probably very similar to what we just did, where I was talking about like excuse me, using a DP solution and taking some sequence. So what's interesting here is that, yeah, you could get a sequence, but the tricky part is you can get a sequence, but the tricky part is the numbers, calculating the amount at each point. I don't know if you could do that for each selection. I don't know the resulting coins for each selection. I don't know if you could do that efficiently. I mean, I guess you could do this in cubic time. So you just take a linear amount of time to figure out, which ones you've already popped, and just, move from left to right on the on your array. Interesting. Yeah. Well, the order that you do it is important. So this isn't the same as a. This isn't the same as a combination itself, or a simple combination. This is actually related to. This is related to. What's I saying? The order matters. So maybe let's see if we can try to solve this using recursion and memoization first. Right? Let's do it that way. So and then we'll do top down, and then we'll see if we can use a DP approach. We'll optimize the DP approach. So okay. You select an index, and now we can dump all of this into a linked list. That might be better. So that way we can remove from the linked list efficiently. Yeah. That's one idea. That would allow us to quickly. We could use a linked list, and that would allow us to quickly determine a doubly linked list. Quickly determine what's on the left and what's on the right. I don't know if that's any better, but that could be good, I suppose. Maybe. What do we want to do? We want to say, pick a number, you get some coins, and then you can pick any of these numbers to start with. And then once you've selected that particular value, you would remove that node from the linked list and recurse on the state that you have. So you can do like a depth first search. Certainly, that's sort of the recursive approach, I guess. Problem with that would be, or a problem with that would be, it might be easier to represent each state as, I think before I had integers, but 500, like which balloons you have left, I suppose. Because you can kind of memoize on that. Like you can memoize on how many balloons you have left, so there's sort of an optimal way to pop these balloons that are left, and there's an optimal way to then pop these based off of those other popped other states. The only problem with that is that the number of ways that you can do this is quite large. Yeah, that's infeasible. The number of possible combinations that you have of 500 is way too big. So you won't be able to. It's way too big, so you won't be able to store all of that, right? So you can't memoize that directly, right? That state. Maybe you can prune a depth first search. Prune a depth first search. So yeah, the depth first search would be just loop through left to right, select a number, and then excuse me. So a simple depth first search would be, exhaustive search would be select from your numbers one of these indices, calculate the value. So if you're running total, add that to your running total, and then mark that spot as add that to a set of could be an unordered set of indices you've already visited, right, marked, and then continue looping, right, recurse with that set and with that total selection, right? So that's sort of your state, is that set and that current total, and then you select again. Also calculating the amount itself too, like if the index you're looking at, you would loop to the left and loop to the right over things that you haven't already selected in order to calculate this number. And yeah, then so you would recurse over all of the indices again, and not select the indices that have already been looked at, and also when you're looking left and right for that index, not select any of the indices you've already selected. And you can loop that way. Like, it's a super simple depth first search, and then you just take the maximum of all of those results. But the problem with that is that it's really expensive in terms of computation. It's actually that would be really like a permutation, right? That would be like 500 factorial, which is really a lot of possibilities to work through. So I wonder if, so that's a brute force approach that works, but is extraordinarily inefficient. It's actually worse than the factorial as well. Slightly worse than that, but it's expensive. So, excuse me. There's a couple of things here. There are a couple of things here. One, the fact that the number is only between 0 and 100 may be relevant here. You might be able to do something based off of that. That makes this a lot more efficient. Very likely that you can do that. The fact that you're going to be removing the balloons also each time you pop them also is probably meaningful here. I want to say these things are probably meaningful, and then also that, like, I don't know, it's a summation that you're trying to maximize here. I don't know. I don't have a solution, or not an immediate one. That would be very expensive, the exhaustive search. So maybe there is something clever that we can do that can optimize the search. That's probably what we need to do. Some kind of clever intuition here. Let's think about it for a minute. What can we do? So what's interesting about this question is the multiplicative terms. It may be the case that we don't need to look at a lot of the possibilities because the multiplicative terms are so much larger. In other words, if you see 100, 100 times 100 times 100 is going to be way larger than like anything else times a 1. I guess any other, 100 times 100 times 1, something like that. And actually so much larger, you need to have 100 times 100 times 1 would have to happen 100 times 100 times 1 would have to happen 100 times before you could get even close, right? Before you're at the same spot. I don't know if that helps us very much, though. I don't know about that. How about, what else can we say and do here? What else can be done? What is, sorry, I don't see the answer. It's the brute force that'll be too slow. Excuse me. So somehow there's a way to do this in a reasonable amount of time. So not really a brute force. So maybe some kind of dynamic programming solution. Select something on the left side, select something on the right side. No. No. You almost never want to select something on the left side or the right side first. And the reason is that you want to get the largest multiple when you pop the balloon, so you want something that's not a 1, at least greater than a 1, greater than or equal to a 1. Yeah, something greater than a 1, and that's not going to happen if it's on the left side or the right side. So you want to do those two balloons last. You always want to do the internal balloons first. But there's so many to choose from. Do you always just pick the? Do you just do a greedy algorithm? You always pick the largest possibility? Well, no, because the sequence you pick matters. Right? If you pick the largest, then there might be not a very large one next. Like if you had 4 balloons to pick from, and you've had to pick 2 middle ones, the large one that you pick first might give you a much smaller one second, and so it might be better to actually pick the smaller one first to load balance, so you get 2 mediums rather than 1 large and 1 small, something like that. I think actually the way that, because we're multiplying, the multiplicative factor here, 2 mediums is actually usually going to be worse than a very large and a very small. I actually think the way this problem is set up, that the greedy approach might just be the way to go. Can I prove that? I don't think so. I don't actually think so. That would be interesting, though. So you can say, let's say there's 1 alpha beta 1, right? So if it's 1 5 3 1, let's try that. You get 15 if you start with 5, and then you get 3 if you then do 3, and that's 18, and then 1 and 1. I think both of those you just add 2, so you get 20. If you did 3 then 5, you would do 15 and 5. Yeah, so actually you would want to take the balloon that is smaller than 5 first, because then you could apply the balloon that is larger, you could apply it twice. That's interesting. So I think actually the optimal approach is the greedy approach. You just take the basically take the balloons in sorted order. You take the smallest balloons first, and not taking the balloons that are on the edges ever. So the internal balloons, you take them, the smallest ones first. I think that's it. I think if you try to do anything else, like the DP solutions, recursive solutions, all that stuff, I think that's just going to be too computationally expensive. And I think you can prove that this is always optimal, because for any choice of balloons that you might have, if you take one of the, you can always prove that you'll get a larger number if you switch that order that I was just describing. In other words, if you have two balloons, one larger than the other, if you take the smaller one first, two balloons that are consecutive, I think they have to be next to each other for this to make sense, but two balloons that are next to each other, you take the smaller of the two first, then you'll always get a larger. Take the smaller of the two first, then you'll always have gotten you'll always get a larger value than if you took the larger of the two first, because the smaller of the two would multiply by the larger one twice, whereas the larger one would only be considered once. Yeah, because you eliminate the larger one when you eliminate it, so you want to eliminate the smaller one first. Yeah, there's a smaller distance between the smaller one and its neighbor. Now, no, not even that. I mean, yeah, it's. Yeah, I mean there's only, so if you have two numbers alpha and beta that are consecutive, beta, the right of beta can be a smaller number or a larger number. We'll call that x, right? So alpha times beta, and then let's say to the left of alpha, we're gonna just consider, we'll just let that be k. So there's k alpha beta x. If you consider beta, if you take beta first, then you have alpha times beta times x, and then you have k times alpha times x. If you remove alpha first, then you have k times alpha times beta plus, so I guess you could look at it this way. I think you can do it this way. I think there's a way you could kind of do a sort. So I think if what I'm describing works, how are we doing on time? Yeah, 20 minutes. If what I'm describing works, I think you could just use like a simple sort to do this. But what you're going to do is, I guess maybe we do want to dump these things into a linked list in order to do this a little bit more efficiently. Excuse me, I'm not really sure how exactly we'd want to do it, but so if you have k alpha beta x, right, and you say k alpha beta, if you do alpha first, plus k beta x, versus k, alpha beta x plus k alpha beta. And k and x are constants, right? But let's say alpha is greater than beta. That means that k alpha beta plus k beta x is greater than k beta squared plus k beta x, which is k beta times beta plus x. Something like that. And then if we say alpha beta x plus k alpha beta, that's going to be greater than beta squared x plus k beta squared again. No, the second one I did wrong. This is alpha beta k and then k beta x. Yeah, there we go. So you're going to get k beta x at some point. I don't know. I'm sorry, it's k alpha x. So you have alpha beta x and then k alpha x. This is larger than this, and this is larger than that. Now that's a good question. What's the second one? These are not the same, so that kind of matters. Alpha beta x is then that's greater than beta squared x plus k beta x, which is beta x times beta plus k. Yeah, these are similar to each other. You can eliminate at least the beta term in both of these when you compare them. But k beta plus x and x beta plus k, how are they related to each other? What we want to say is that one of these is larger than the other. It's always larger than the other. That's what I want to say. If that's true, then that means we can at least always select, for consecutive numbers, we can always select which ones we want to pick first. I think what I was saying is generally true, that you would want to take the smaller numbers, smaller balloons first, because the larger balloons next to it, you'll be able to use them more than once. You want to be able to use them as many times as possible. I think that's the right idea. You don't want to take the outer balloons at all, ever, because those are always going to be paired up with smaller multiples. So you just take the inner balloons. You take the smallest ones first, and then use a greedy algorithm. The outer balloons, you leave those for last, and you just take the. You would, for the smaller balloons, you would still want to take the larger of the two first. But I don't think, I mean, even with that order set up, it still takes a little bit of time to calculate what that would look like. And then also, how do you prove that that's correct? That's a tricky thing here. That you would pick beta before alpha no matter what k or x you have. You want to prove that this is always smaller than this one. And then you want to extrapolate that to what I was describing, that you want to take the smaller ones first. So this is k alpha beta x. If you take alpha first, you have k beta x is the next one. So k alpha beta, or you could do beta alpha x. Let's just say that k is greater than x. Let's start with that. Or it could be equal, but we'll just say it's larger. So k is greater than x. So we'll say beta is beta. If you take beta first, you have alpha beta x, and then k alpha beta. Okay, so let's say k is greater than x and alpha is greater than beta. So if alpha is greater than beta, this is, how do we compare these? So clearly k alpha x is greater than k beta x, right? That we have immediately from alpha greater than beta. But the other two, how do you compare alpha beta x to k alpha beta? Well, if k is greater than x, then this is larger than x, and so this one will actually be larger than this one. Oh, I see. And if k is less than or equal to x, then this is less than or equal to this one, because these are the same. Because this part is the same. That's when you relate k alpha beta to alpha beta x. Yeah. So in order for this one to be a better choice than this one, you would need to have a significant difference between each of these. Alpha beta k and alpha beta x. Yeah, there are different sequences that you might have depending on. So it's clear that if x is greater than k, right, or if x is greater than or equal to k, then it's clear that we would want to take the other one first. That we would want to take the smaller of the two first. So this is. Or no. Did this wrong. X could be greater than or equal to k, and then x could be less than k. So alpha beta x plus k alpha x, if you're in this situation, alpha is greater than beta, and k is less than or equal to x, then which is a little bit confusing, then this first one is always going to be the right choice. So it's clear if, let's do the other way around. Let's do k. How does that work? It's if k is less than or equal to x, so you're going to maximize on x in this case. So what's interesting is that you have alpha x twice, and here you have k beta twice, right? So you have k beta times alpha plus x, or this is the choice that you have to pick from, alpha x times k plus beta. So what that means is you're actually going to optimize on this choice between these two is going to be optimized on this multiplicand versus this product. Which of those is larger? That's the one you pick. That's how you decide. Because, well, what's interesting about that though is it's not necessarily maximizing one or the other, because this, I mean, even though this is adding, right? So, well, all these numbers are at least one or larger. These are all positive numbers. I guess what I'm trying to say is that like this multiplicand could be, I'm actually not sure. Now I'm thinking about it. These are your options, right? So you probably want these to be the two largest numbers. So you have four numbers. You probably want these to be the two largest numbers, and these to be the two smaller numbers. Excuse me. And the reason is that, I don't know, if you did like k, or not k, but just like y times x plus z, or x, y plus z, or z, x plus y. Which of these is going to be larger based off of x less than y less than z? It's kind of a similar question to what we're asking here. If x is the smallest value, and even though this is very large, I don't know, is that, I don't know, let's take some examples. You do like 1, 2, 3, right? If you put 3 over here, that gives you 9. If you put 1 over here, that gives you 4. If you put 2 over here, oh no, excuse me, that gives you 5. If you put 2 over here, that gives you 8. These are pretty close. But yeah, it seems that the multiplicative factor is the best. I don't know how you like compute that, show that that's always the better one to increase is the multiplicative factor. Because what's weird about this is that you are increasing a multiplicative factor here when you increase one or the other. It's just you're adding first before you multiply. In other words, there's like 3 different multiplying factors here, and you could add 2 numbers together and then multiply. I'm trying to think how to. It's not an additive factor. That's, I guess, what I'm trying to say. It's not. You're not adding this factor. You're adding this factor times this other factor, and times both of these. I guess maybe the way to look at it is that every change in k and b is applied twice, whereas every change in alpha and x is only applied once. Maybe that's a better way to express it. I think that's exactly what I was saying about the balloons popping, is that like if you don't pop, if you leave the balloon around longer, it'll be available to be popped, to be used in another calculation longer. So you want the largest balloons to hang around longer. You actually, it can only be used, no, it can be used multiple, because you could pop other balloons against it. Yeah, that's the way to think about it. So you want those are the largest balloons to hang around longest, and that's exactly why. Is that that's not the most obvious. Like, it's kind of hard to explain that or express that. Like, I don't know how to explain that rigorously. But yeah, I guess you would always want to leave those balloons around longest. I don't know. It seems weird that would be the truth, but it seems to work that way. Yeah. Yeah, I mean that's kind of it. So you would pick the larger pair of k times beta and alpha times x. That's what you would select over the two of these. So depends on which of these has the largest multiplicative factor. It's also what's interesting is the additive factor too. Like you want alpha and x to be the smallest numbers, or k and beta to be the smallest numbers. Now, if alpha times x is equal to k times b, then you have alpha plus x compared to k plus b. If alpha times x and k times b are equal to each other, does that imply that these two are equal to each other as well? I mean, you could do like 5 times 2. What is something that two multiplicands are equal to the same number? Like 18. You could do 2 and 9, and you can do 6 and 3, right? These are all different numbers, so you do 2, 9, 6, and 3, and so you can end up with 18 times something and then 18 times something else, where k could be 3 and beta could be 6, so that would be 6 times 3, and then the other side could be 2 times 9. So 2 plus 9 is 11, 6 plus 3 is 9. You would so 2 times 9 is a plus x, and then 2 times 9 over there, 2 plus 9, 2 times 9, and 6 plus 3, 6 times 3. And then you get oops. Hold on a second here. Okay. So which of these is better though? 2 plus 9 is better than 6 plus 3. Why would that be the case? 6 plus 3 only gets you to 9. 2 plus 9 gets you to 11. 11 is better than 6 plus 3, or larger than 6 plus 3. But why? So that would be 2, 9, 6, and 3. Let's take a look at that case. 2, 9, 6, 3. And we said k and beta. So 6 and 3 should be paired. So we could put 6 and 3 here. And I was suggesting you want to do 6, 3, and 9 plus 2, 9, and 3. And that's better than 2, 9, 6 plus 2, 6, 3. Yeah, this 3 is larger than 2 here. So in this case, you would pick 6 first. What about and what were these situations? This was 11 times 18, 2 plus 9 times 18. 2. So that's actually not the, well, so this one is 18 would be 2 and 9. And then this is 2 times 6 times 3, which gives us 2 plus 2. 6 plus 2 times 18. And this one will be 12, right? It would be 9 and 3 times 18. Yeah, if these get paired off, right? Those are the two considerations. So 8 times 18 and 12 times 18. Yeah, 9 here and 3 here. But how about another situation where you get, we're saying 9 and 2, right? So it's a 2, 6, 9, 3. How about that scenario? Yeah, 11 and 9, right? That's what I was suggesting before. So I was saying the rule is we want to start with the smaller one first. So 2, 6, 9 plus 2, 9, 3 versus starting with 9, which would be 6, 9, 3 and 2, 6, 3. And this one would give you 11, right? 2 plus 9 times 18. And this other one gives you 9, 6 plus 3 times 18. And the first one is the one that I was saying we want. Is that always true? I mean, it just doesn't seem. So 2, 6, 9, you would say 2 and 9 is 18, so 6 plus 2 and 9 is 18 again, 3. So actually this is wrong. This is not 2 and 9 and 18. This one is actually 2, 6, 9, and then 2, 9, 3. 18 is 3 plus 6. And this other one then is, so you pop 6, 9, 3, pop 9 first, get 6, 9, 3, and then pop 6 next, you get 2, 6, 3. And this will actually give you 2 and 9. So my idea was wrong. Here's a counterexample for the idea that I was thinking. Right, because this gives you 18 and 2, and this gives you 18 and 9, and that gives you 9 plus 2. So this is actually the one you would want. 11 times 18, not 9 times 18. And this other one is, so it works in this case with 2963. You can do the smaller one first, but 2693, if you do the smaller one first, even though 9 is available for both of these, it's actually better to use 9, 6, and 3 in one spot, and then take 2, 6, and 3. Yeah, for whatever reason, the absolute largest is the best to take to start with. So I think that really simple, basic, like super greedy algorithm might be the right one, which is just maximize the largest take you can get at each step, and do it that way. That might be it. So yeah, 963 is the absolute maximum in this case. And the reason is that you have multiplicative factors. So because you're multiplying each of these pieces, it's best to oh, excuse me. Because you're multiplying each of these pieces, it's best to, what was I saying? Because you're multiplying each of these pieces, it's best to just take the absolute maximum. It'll pretty much always give you the best possible. I think it's that simple. I think just like a really simple, greedy approach is what you need to do. I could be wrong about that, but let's try it. So this is not too bad. We can compute that. That would take linear time. Oh no, excuse me, quadratic time. And it's quadratic time, sort of linear space, because you just have to store like the remaining numbers. You can actually just have like a set of numbers you've already selected. That's simple enough. And then Vince, we'll just say used. And we can say really while use.size is less than nums.size. We can say for int equals 0, I is less than nums. If use.count of I, if not, then we can say current max, some value, and then index, max index, current index, start with a -1. If not used, then we can calculate val for this particular balloon. It's going to be nums of I, and we'll say A will just be I is greater than 0. Do nums of I minus 1. Or 1. B is similar thing. So we have plus 1. I is less than. You can also say this. Just make that n. I is less than n minus 1. And this will be b. And so we can say a times nums of I times b. And say if val is less than current max or greater than current max, then now what's interesting about this is actually this can't be correct, because you could have situations where you have the same maximum twice, but it's better to select one balloon rather than the other. Now maybe I'm wrong about that. Maybe I'm wrong that it doesn't matter actually in those cases also. But I get the feeling this is not going to be a correct algorithm. Something tells me this is not going to be correct. We could try it. So update the current max and update the current index to that value, And then after we do that, then we'll say used, insert current index. We'll say ret at the end. Ret plus equals current max. So use that balloon, and we'll skip it next time around. And that's it. Yeah. So then return ret. And I think that's it. I think that's all you do. See, that compiles. I think it's that simple. Wrong. Okay. Of course. Yep. So 3158 just doesn't work. So we picked the largest possible. We would. That would be 158 would be the first one, I think. So this is just immediately wrong. Yeah, 40, 158, and then you pick the next largest, which is probably 318, which is 24. So you get 40 plus 24 gives you 64, and then 3 and 8. Next largest will be 318. Actually, both of these are the same, but you get 24 plus 8. Is that what we did? So 40 plus 24 plus 40 plus 24 plus 24 again plus 8. Yeah. And then you have to add, oh no, wait. How did we get 98? How did that happen? I said the maximum at each point, right? Let's get 3, 15, 40, 40. I think it starts with this one. So 318. It's 40. And then 3, 24, 8. I think it's 24. And then 24 again. Oh no, how come we got that's interesting. Actually, kind of curious how I got here. I don't really have an answer, by the way. This problem, I don't know. 40, 40, 15, 3. Oh, how do we get 40 twice? Really? No kidding. 40, 40. Whoa. 40, 40, 15, and 1. Huh. Or 3, rather. Oh, so 3 and 5 were left over. Oh, so I guess that's kind of weird. So we took 8 first? Is that right? How did that happen? That doesn't seem right. 0, 1, 2, 40. 0, 1, 2, 3. Oh, that's why. Oh, I see. Oh, no, no kidding. I forgot. I did this, calculating this wrong. Actually, maybe my algorithm could be right. I don't think it's right, but it could be right. I don't think so, but oh yeah, I'm calculating this incorrectly. You actually got to go. So this is not the most efficient way to do this. I think if we dump everything into a linked list, we can make it more efficient. But so 400 cubed. Yeah, that's gonna be too slow. But yeah, we can make this cubic. So we'll just int a equals I. A is greater than 0. Decrement a. Say if used dot if not used. Or actually, you want to do it the other way around. You want to say a, and so it starts off at I minus 1, as long as a is greater than 0, and not used dot count of a. Yeah, keep decrementing a, and you'd say we could just say like L, say is a is greater than 0, then take nums of a, otherwise take 1, and you do the same thing on the other side for b. B starts off at I plus 1, b is less than n, and keep incrementing b. As long as it's less than this value and it's already been used, then we're going to keep moving b. I think it said r to b less than n. Take nums of b, otherwise take 1. And the value is going to be L times R times the num. There we go. Okay, something like this is more of what we're after. Don't know if this is correct though. I don't think this is going to be correct still. A little more. Hi friend, hello, welcome, howdy. How are things? How are you? How's it going? This is what I meant to do. It's still wrong, but it's a little bit better. So now what we get is index and the value. So I don't have a solution to this problem, by the way. I'm like totally unsure. I don't really have a good one. I'm just kind of guessing it. I think there's some kind of like greedy approach that you can use. I don't think I could be wrong, but I'm thinking that a dynamic programming approach or like a recursive approach is not going to work, just because unless there's a way that's like clever that I'm not seeing, not realizing. But I think it's just there's too many. Excuse me. You know, I did as I went. I got stuff out of my car and I sweat just a little bit, and now my underarms are. Now I gotta go take a shower. But what was I saying? I think there's a way to do this using a greedy approach. The brute force approaches that I thought of just kind of fell apart. They're too difficult. Maybe I'm thinking there's got to be some kind of optimization, either A, to make the brute force approach more efficient, to make it sort of like memoized, or B, there's a way to do this that is like like something that's like not even a brute force approach, not an optimization at all. It's just like a flat out like greedy algorithm, something like that. The reason why I'm thinking that is because these multiplicands, you've got each part is multiplying. But I think, oh, so yeah, so this is what I thought my algorithm was going to do. So index 0, 1, 2, it should pick here, and then you only have 3, 1, 8. Then actually it goes with, oh, that's really interesting. 0, 1, 2. Wait a minute, what? Huh. How do we get 8? I would expect 40, 8, and 24. I was actually expecting 40 and 24 would be the next one. It would still give me the wrong answer, but I'm wondering why my code doesn't do what I expect it to do. That's So 0, 1, but we burst 5, so 3 should be nums of a is greater than 0. Oh, excuse me. That's why. There. Slight mistake. Okay. Wait, what? So we should get 5 times 8 times 1 is 40. Remove 5. You get 1 times 3 times 2 is 8. It's 24. Then you get 3 and 8. Right, you get 24 again because you pick 3. And then finally you pick 8. It should be... Now, that is... oh, this is also greater than or equal to 0. Yeah. There we go. That's what I was expecting, 96. That's what I got the first time. Calculated that so many times. I got 64, 88, 96, and I kept thinking, how did I get 98 before? I got something wrong. But so obviously this is not a correct algorithm, even though I managed to get this to do what I want. This would be cubic time to calculate this. You could optimize this with a linked list, I think. You could put a linked list in here and then remove the nodes as you process them from the linked list. That way, a doubly linked list, that way the index you're interested in, the two values to the left and to the right are right there immediately, so you don't need for loops here. Still be quadratic time, but it's still a wrong algorithm though. That's the problem. Optimizing it's not really. Kind of doesn't matter. Right. So, excuse me. I'm wondering. Maybe there's like a stack-based approach to this. Maybe there's a dynamic programming approach. There's some trick here that I don't see. That's got to be it. There's something clever here that I'm not realizing. It's the only way. It's the only way. Let's see. My thinking was just always take the smallest balloons first, the smallest internal balloons first. That works on this case, but I don't think it works in general. I think I proved that before. If you have something like this, right? So you could do 2963, and you can do 2693. If you take only the smallest internal balloons first, you'll go 1 and 2, and and 1 and 2. But the problem is that this gives you 296 plus 263. Or no, excuse me, other way around. 263. So it works. It works for this. Excuse me. It works for this case. 2963. This one checks out. So you would do 963 plus 293, which would give you, what did I say it was? It was 9 times 18, 9 plus 2, 9 plus 3 times 18. Right, this gives you 18, and this gives you 18. That gives you 12 times 18. As opposed to all the other choices, which were, if you pick the left or the right side, they're suboptimal to start with. And also picking the smallest of the, you could pick the other way, you pick the larger of the two first, will give you 296 plus 263, which gives you 6 plus 3 times 18. No, 6 plus 2 times 18, which is 8 times 18. Right, that gives you 18 times 6, 18 times 2. Yeah. So, but if you do that on this side, right, if you go 269 plus 693, that gives you 6 times 18 plus 9 times 18. I'm sorry, yeah, 9 times 18. No, yes, 18, 18, yep, yes, 6, so 269 plus 293. Mm-hmm. 6 plus 3 is 18. That's a 9 times 18. As opposed to, if you go with 9 first, you get 693. So this one is incorrect. 693, go 9 first, you get 693 plus 263. And that gives you 9 times 18, right, that's 18, 9 times 18. And then this is also 18. No, this is 18. 18 times 2, so 9 plus 2 times 18, which is 11 times 18. So this is the one you want to pick first. So you would want to take 9 first. So that is really tricky. But basically what it comes down to is you cannot do the simple greedy approach that I was describing, where you just take the smallest internal balloons first, is incorrect. Now it's clear that you take one of the internal balloons first, but it's not necessarily the smallest internal balloon first. Not in all cases. At least in this case, it doesn't work. Is it in most cases? Maybe. The idea is that you want to leave up the largest balloons for as long as possible, so that you can multiply by those in your other calculations. That's the idea. Why it doesn't work in this particular test case is because there's a multiple to the side of that largest balloon that's large enough compared to the other balloons, such that it's actually advantageous to multiply by that balloon by the largest balloon. I don't actually know how you would express that. It's just, I guess it's better to multiply by these three first, and then multiply by these ones, as opposed to multiplying by these three first, and then multiplying by these ones. It's weird to think about that, why that might be. I guess the easier way to express it would be, easier way to think about or express it would be that you're comparing these two expressions to each other. So it is actually possible for, like, you want to maximize these pairs of numbers. So in this case, the maximal pair is 2 plus 9 is larger than 6 plus 3. So because you're picking 2 and 9, that pair implies you pick. So this pair corresponds to, I think, selecting so it's these two. Yeah, it corresponds to taking beta first. And then this corresponds to taking alpha first. So if k plus beta is greater than alpha plus x, that implies beta first. Otherwise, alpha first. At least in this case, right? That's the kind of discerning maths you would do, I guess. And otherwise, if they're equal, it doesn't matter which one you take first. And the reason is, yeah, so beta times alpha times x plus k times alpha times x gives you alpha times x times k plus beta, right? So you take beta first, that corresponds to k plus beta, and alpha first corresponds to alpha plus x. Yes. So that's how you figure that one out. Now, okay, so I guess we sorted it out for when k is, not k, when n is 4, when you have 4 numbers, this is how you can decide which one to take first, and then obviously you take only the middle ones, so the other selections kind of resolve from there. But what if you have another case? What about, excuse me, oops. What if you have k, a, b, c, x? How about this? Can you make the same claim? Well, you could definitely say that if you're considering these two situations, and this situation, right? The deal that you have going on here is you can make, if you were to decide between these 4 which to select first, it's clear if you take A or B, depending. So in this case, in other words, these give you 2 subcases that you can decide which one to select first from if you're going to go down that path. But really the question is which of these 2 should you, in other words, you have to pick one of these 3, and one of these selections, and then one of these 3 numbers given those 2 selections. So here you would have the choices between k plus b compared to yeah, so b. So if k plus b if this is greater than a plus c. Otherwise, a, right, select B, select A, and then in this other case, it's A plus C, if A plus C is greater than B plus X, then you'd pick C, otherwise pick so you have A plus C greater than B plus X, you pick C, otherwise you'd pick B. But the question here is, okay, if you do those things and then both of those resolve to another selection of four elements that you would know what to pick from to maximize the result. But the question is, which of these should we pick? Like, should we pick one of these four, or should we pick one of these four? And I'm wondering, I don't actually know. I'm wondering a couple things. Like, one, if maybe this could be something we use like dynamic programming for, or if maybe this is something we use dynamic programming for, or I'm trying to think this through. Maybe there's some like brute force approach we could take from here, where we're selecting from two different starting points, right? Either this starting point or this starting point, and we can kind of recurse all the way down to what the final result would be, and then just compare the two. Kind of take the maximum of those possibilities. But the problem with that is that that's still kind of like a depth first search type of deal. We're kind of updating and modifying the state as we go from one to the next. It's really kind of not too different from just selecting a balloon or not. This is a tricky question, man. I don't know. Not obvious. There was a similar question to this, which was like, instead of selecting a balloon, you would select from the left side or the right side. That was the can I win question that we were looking at before. And I think I forgot how I ended up solving that. I think I did I want to say I used like a game theory solution, something like that. This isn't the game though, this one. Excuse me. I don't know. Haven't got a solid solution. Let's think about this for some time. I got some balloons. Need to burst them in the optimal order such that you get the most points. And there's a function to calculate how many points, and that's related to which balloons are nearby that are remaining. Okay, interesting. So yeah, I mean, it's kind of lends itself to a linked list. This type of solution. Excuse me, a doubly linked list. But the problem is, yeah, the state, like the balloon configuration changes every time you pop a balloon. Huh. It's true. And all the different possible ways you can have the balloons set up, I believe, is combinatorial. Yeah, it's true. There's a each. So depending on the number of balloons that are left over, it's a combinatorial number of ways to actually set up those balloons. Excuse me, in that situation. So trying to brute force by calculating every possible combination from the bottom up is probably not the best approach. Now, what's interesting is that maybe you could do that. Maybe you could start with, okay, if you had one balloon left, what would the number be? And then from there, let's say there's two balloons left, and what would your kind of current largest value from right to left, so to speak, or from back to front, what would that be? Excuse me. The problem with that is, while it might work, so you'd go from one balloons to two balloons, three balloons, etc. It's all the way, recreate all of the balloons back to the beginning. The tricky thing with that is, and yeah, I guess these could all be linked lists. And indeed, it would be a quadratic time algorithm, and it would take quadratic memory, I think. Yeah, you can make it linear memory. You only need to keep track of the... Oh no. Actually, I'm not sure about that. I'm not sure if it would be quadratic time. Excuse me. Thinking about that. Well, okay. Well, certainly a brute force. Well, no. So there are some problems with that. Even the formulation of the idea is kind of awkward, or not complete. So you could start with one balloon, right? All the different ways you could have one balloon, which there are n of those, and then you can have all the different ways you have two balloons, and there's some number, right? So if we sort of undo the popping, or suppose that we're going to pop that balloon, we could figure out what the resulting value would be, right? And sort of associate with each of those pairs of balloons with a number. Excuse me. For each of those, we can then add another balloon, doing the same repeated routine, but each of those would create then combinations of three balloons, which again, it's a combinatorial number of them, right? And choose three. And then we can go to 4, 5, 6, and just keep going. And all of those different combinations would have an associated number. And then we can go all the way to the end, and then take the largest number. And that would be that. Now again, that gives you an exponential number of sets, I suppose. What's kind of interesting about that is the sets will actually start to come back together again as you go from right to left. The sets will start to re-merge, I guess. In that case, you could just take, excuse me, you could do kind of some sort of dynamic programming on the sets that are being generated, so that you take the smallest number for that set, and then finally at the end, all the sets will combine into one. You take the smallest number for all of them. Yeah, that's all well and good, but the problem with that is that this number is gigantic, right? That gives you you'll have the largest combinatorial number of sets at any intermediary stage, and with a number like 500, excuse me, the longest combinatorial number would be between 500. 500 choose 250, which is an exceedingly large number. Yeah, it's a big number. So that's too big. Excuse me. I think so, actually. Let's check. I'm fairly certain that number is enormous, though. It's 500 factorial divided by 250 factorial. It's squared. Yeah, that's still enormous. 150 zeros. That's a lot of zeros at the end of a number. I don't know, man. I don't know. Oh, my body. Oh, okay. Okay, so what would be some other ideas? So that works, but it's incorrect, right? Now, one idea would be maybe to prune off some of these. So, yeah, I mean, clearly any solution that doesn't begin by popping the end balloon, or yeah, any solution that doesn't any solution that starts by popping one of the end balloons is going to be incorrect. Like, there's no way that could be the maximal, unless all the balloons are ones. Then it doesn't matter what sequence or order you pop them in. As mentioned, all of the different possible sequences are permutation of sequences. So 500 factorial different ways that you can pop the balloon, so to speak. And as mentioned, you can slightly improve that by considering how many different ways you can get to a certain combination of balloons and taking the optimal approach for that particular combination. And you can, as mentioned, you can do that recursively. But that's still, there's combinatorial number of ways to get different combinations. So maybe you ought to pick the maximal at that point. Now that wouldn't work either, because even if you could somehow do that, because the actually no, you might no. Yeah, you have to pick the maximal per combination, because there could be different ways to get to that combination, but the other combinations have a similar sort of a problem, sort of an issue where there's multiple ways to, from even the optimal previous combinations, there are multiple ways to get to the next combination from there.
and by adding balloons or removing balloons, however you want to think about it. And actually, we can go left to right too. That works as well. I mean, there's sort of multiple for each combination. There's multiple ways to reach the next combinations. Multiple ways you could have popped the balloons. Although it is interesting, at least, to note that there is kind of like a you can say that there is an optimal way to get to a certain configuration of balloons, and you'd want to take that optimal way every time for our problem. That's some intuition there, I suppose. But the question is, how can we optimize this further? Somehow optimize this further. Somehow not go through all the combinations, all the permutations. You've got to. I think you would be required. You would need to somehow eliminate possibilities, like eliminate certain combinations, knowing that they would not give you the optimal answer. Somehow eliminate those things ahead of time. Hmm. What can we do? What can be done? Um. Sorry. I don't have a solution, but I also have some other thoughts in my mind too. Um, hmm. What do we do here? Um, hmm. Hmm. Gotta think here. Um. Hmm. Um. Hmm. What other possible approaches could we think of? I don't have any ideas. Um, well, wondering, yeah, that one idea was like maybe there's a way to do this that takes advantage of the fact that the balloons, the values themselves are between 1 and 100. Maybe there's something that can be done there. Hmm. Maybe. Um, hmm. Hmm. Well, that idea that I had before with the combinations, I mean, there's some obvious redundancy there when you're dealing with only 100 numbers, because some of those possible combinations will have duplicate numbers, um, and those numbers will be, like for instance, you could have 5 numbers that are the same next to each other, um, and so all the different ways you could pick two, 3, 4 numbers out of those 5 numbers because they're all the same number. Um, those reduce to only a few different considerations, right? It would only be 1, 2, 3, 4, 5 of them. There's only 5 possibilities. Whereas if you have 5 different numbers, the number of ways you can select 1, 2, 3, 4, or 5 of them, the total number would be 2 raised to the 5th, right? Exponential number of ways you could pick some subset, some combinatorial subset. Whereas the combinatorial subsets, if they're all the same numbers, there's only a linear number of them. So there's some optimization that can happen, and that's a pretty big optimization, right? That takes you from exponential to linear, right? That's a logarithmic. That's a big deal. That's a big difference. I don't know though. I don't know. Let me take the headset off and put on the charger. I'm just kind of ponder for some time. I really don't know. Really don't know the answer to this one. How this could be optimized. I'm thinking some kind of deep. It's got to be some kind of DP way of doing this. I don't know it though. Let's have some buzzing noise for some time here. Yeah, I gotta just keep pondering it. I don't know. I'm gonna put the headset down.
So I think I'm going to make this part one. We'll go ahead and make this part one. I don't really have a solution. Sorry I spent 2.5 hours on this. I think we'll take a break. So yeah, so interesting problem. I didn't make it, didn't get there. We got part one. I need to use the bathroom. I really need to use the bathroom. So yeah, thank you for watching. Talk to you soon. Have a good rest of your day. Make this part one. Maybe come back tomorrow. Not tomorrow. I'll just take a break for some time. Think about it. Maybe come back if I have some inspiration, some idea. Come back to it. But all in all, I don't know, man. I don't know what the answer would be. This is kind of a challenging question. I really gotta go though. I really gotta use the bathroom. All right. So thanks for watching. Talk to you soon. Have a good day. Bye.